Hello and welcome back. Today we are discussing section 2.5, marginal analysis and approximation using increments. First video we're going to tackle study marginal analysis in economics to try to figure out what that means. So we'll start with an example. We'll reuse a function that we had in the previous section from the chain rule. So productivity for some product is given by this P of W thing. The input is worker days, so there's W, and the output, this big expression, is what productivity we could expect. So that's in items produced. So the first thing we're supposed to figure out is to compute and interpret this expression. This is a little bit unusual because we generally interpret when we've got actual values rather than variables plugged in, but it turns out we can still write something meaningful here. And then we'll do this for an actual concrete value. So for 6 and 5, we'll figure out P productivity difference, and then we'll compare this to whatever the derivative is. Okay, so first things first, we'll take our two big expressions here. P of W plus 1 is this first set of brackets, or first set of things in radicals here. And then P of W should be the exact same thing that our production function was to begin with, no changes. So that second green box thing ought to look identical to what we started with. This one is a little bit different, but we just have to remember how evaluation of functions work. W plus 1 means that I should find all the w's there before. So where w was getting squared, now w plus 1 is getting squared. And where w is getting multiplied by 30, now w plus 1 is getting multiplied by 30. And then there's a little bit of simplification we could do. So some FOIL here, w plus 1 all squared out. That times 3 gives us these first terms. We'll run out of colors, but I'll give it a shot. So this first, all of that is this FOIL piece expanded right there. And then 30w times 30w plus 30 times 1 gives us this last set of terms here. And then there's not a whole lot we can do with that second radical. And there's not any great ways to combine two different radicals separated by subtraction. So not much to do there. We can simplify a little bit underneath this first radical to get 3w squared plus 36w plus 33. But that's about it. Okay, so then all that's left is the interpretation piece. And what we should note is that the thing we did was look at production at a particular level of worker day, particular labor level, and then we increased that labor by 1. So this should be the difference in production levels when we increase labor by 1. So that's exactly what this is supposed to say. So this is difference in productivity at one greater worker day compared to wherever we started out. Part B, we're actually doing this concrete computation. So although it may not look like it, we actually are using the same function expression thing that we had just a minute ago. This is, we can imagine, our starting value of number of worker days, starting value for labor. And then if you add 1 to that, you get 6. So this really is P of W plus 1 minus P of W. That's that same thing we were doing in part A. But here we have the advantage of getting a concrete number that a calculator could help us out with. We were then instructed to compare this answer to the derivative, P prime of 5. And here it will be a little bit cheap and just remind ourselves that in the last section, we had this exact same function and we computed its derivative. We figured out that P prime at 5 was 2. And then what I'm supposed to note is basically that 1.97 and 2 are pretty darn close to one another. And this isn't an accident. What's going on here is that when we ask for the actual difference in output, then the derivative is trying to give us a good estimation for this number in general. Our interpretation of the derivative goes something like this. At 5 worker days, we would anticipate the rate of change in productivity to be 2 additional items produced for every 1 additional worker day. Basically that slope thing. If the input goes up by 1, the output goes up by this much. And this is a pretty good approximation. 1.97 is close to what we guessed the increase to be. So we'll formalize this using kind of a theorem, as it were. So if we have big numbers for x in particular, so this becomes more accurate if we're looking at the difference between 1,000 items produced and 1,001 items produced versus 5 and 6. But as you can see from the last example, it can still be pretty accurate. So what we see is that this actual rate of change, or this actual change when we increase units by 1, can be approximated with the derivative. So this is one excuse for using the derivative. And then just for the visual, let's compare. So what we have here is the tangent line approximation to our, let's say it's cost function for C. So if this is the cost function, our tangent line is guessing that our output, if we go over 1 from this starting point, we will go up C prime. So this is our output. Well, okay, that's not actually the output. The output's really up here on this pink part of the graph, but this is an approximation for it. Then if we actually went over 1, then the distance up would be this real difference. Here we have some starting height, and then it goes up to this height. So the difference between them would be this cx plus 1 minus cx naught. So the actual height at x naught and the actual height at x plus 1 subtracted. So it's not always as bad as this picture implies. That this blue line is way below the pink one. This is kind of blown up to just be able to see the picture a little bit better. But that's the goal. This height is trying to be an approximation for that height. So additional set of definitions: marginal costs, marginal revenue, marginal profit, marginal blah, basically. So if we say marginal blank, we're trying to imply the derivative of blank. And just to compare with a 200 level econ course you may have taken or may yet take, they generally define, say, marginal cost to be the difference in cost when you increase unit production by 1. And that's fair, but if you don't have a derivative calculation, then that's as good as we can get. But since we've got derivatives, we can define marginal cost to be the actual instantaneous rate of change. So just to put this in writing, so marginal cost, we'd have C prime of x, where x is how much we're producing. Marginal revenue is R prime. Marginal profit is P prime. And then let's try out an example with this. So I don't think this one is way off base. If we imagine the cost to produce, to farm A acres of a soybean farm is that function there, 0.01 A squared plus 480A plus 1,200 bucks. Alan has a 400-acre farm and wants it to grow. So our job is to use marginal cost to estimate this increase. And then we'll try to say something about marginal average cost as well. So we have to remind ourselves how to get average cost, but that's not too bad. So part A. So the marginal cost, we were told, is the derivative, the rate of change in our cost function. So C prime, we would take derivative with respect to A of this whole deal. So that's not so bad. We've been doing stuff like that for a little bit. So power rule would bring the 2 down. We'd have 0.2A, 480, and then the A would be gone, and so would this constant. So basically we can say, let's use this marginal cost to approximate what the actual cost would look like at 401 acres. So C prime of 400 is an estimate for how much we would anticipate this thing growing. So we take 400, dump it in for our acreage, we get 488. We'd say, okay, well, we would anticipate that since cost is in dollars, increasing our input by 1 would increase cost by about that much. So in other words, the next acre would, our approximation says, would cost about 488 additional dollars on top of whatever he was spending to farm his current land. So part B, so we're supposed to figure out marginal average costs. So I guess we need to figure out what average cost is. So if you recall, average cost looks like the total cost function divided by our production level. So our production level is a little bit more interesting in this case. So instead of producing items, we're sort of making acres, if you will. So C of A over A looks like our original cost function on top. So this piece on top is just cost, the thing we were given in the original problem. And then with a little simplification, dividing A into each thing, well, okay, A doesn't go into 1200, so we still have a 1200 over A when we're done. But at least it comes out of these other terms. The alternative was, if we have to take a derivative of something like this, is to use quotient rule, which is, I don't know, just not that much fun, if we can get away with it. Sometimes it's necessary, but. So marginal average cost would take the thing we just found and take its derivative. So we just arrived at 0.01A plus 480 plus 1200 over A. So we'd like to take the derivative of that. One quick reminder that's useful here, this expression could be rewritten so that it actually looks like some power rule. Because right now it looks like we'd have to do quotient rule. But since A is in the denominator by itself, we could really write this as 1200a to the -1 power. And then that's all set up for power rule to work very nicely. So the negative would come down, so that would change the sign over here, and then our exponent would be reduced, so we'd be down to a to the -2. And of course, since 40 is a constant all by itself, it's going to go away, and then 0.01 times a would have a rate of change of just 0.01. So this is our marginal average cost function in general. If we actually dumped in 400, then we would see how much we would anticipate average cost changing for increasing by 1 acre. So here's a 400 dumped in for our acreage. It's about 0.0025. And then our interpretation of that is average cost. So again, we're just doing our typical derivative interpretation. So average cost per acre, this is the function that we were asked to study. That's just AC. So I'm just parroting back what this function actually represents. So average cost per acre is anticipated to increase, and that's because the derivative was a positive number. So AC prime was bigger than 0. That's going to imply that this function is growing, which makes sense. It seems possible that average cost could increase. So, and it's increasing by, well, okay, so this was in dollars. So if I move this over 2 spots, I should get cents. That's still 1/4 of a cent. Not so bad, but if we increase the total acreage by 1, we're anticipating that we would go up by 25 cents per acre. So that's not a huge increase, but that's what this predicts. So this is these processes are commonly referred to as marginal analysis because we're using marginal cost or marginal average cost to make some sort of statement about these functions. We'll be back in the next video to talk about approximation by increments. Thanks for watching.